Right, so there you have it. There you can see the OKACM delta, and there's the Tomalakani fault, there's the Vineri fault, there's another fault up here, a very small one called the Gamari fault, which marks on this side, and that's a panhandle, and there we have the delta. Now, if you look at the contours, this was the first detailed contour map created by a colleague of mine, Tommy Skumbrick. This predates the shuttle radar, and I'll go back into the details, but you can see the curved form of the OKACM. And the important thing about this is we call it a delta because it's sort of reminiscent of the delta, you know, that kind of bird's foot pattern that you see like the Mississippi Delta. It's not actually a delta at all. A delta forms when a river carrying sediment flows into a lake or an ocean, and then because of the cessation of the flow, the sediment gets deposited. So the delta builds out, and the top of the delta is at sea level or at lake level, it's flat. That's the delta. This is not like that. This is a sloping surface, and it forms when the water flows in a confined region like the panhandle, and then it is released to spread out sideways. And it's the dispersion of flow that causes a loss of energy and the sediment is deposited. So it forms a conical surface, which you can see in the context. And that is called an alluvial fan. So OKACM delta is not a delta really, it's an alluvial fan. We call it a delta. And same with the linearity, it's just a smaller version of it. And they bounded in the south by the big faults here and in the north by faults as well. Okay, so we're going to look now at the delta now. It's constructed next slide. This delta is flat and it's smooth rather, not flat, it's sloping, but it's smooth. And Thomas Gumbricht here just worked out how smooth it was. He took from his contour information, which was a very high resolution topographic map, he looked at the elevation along these arcs here. That's increasing distance from the apex of the fan over there, lowering the panhandle, and then he plotted these out. He stretched them out and he plotted them as lines here on this scale. So there's the elevation, and these are the actual. This is meters above sea level. These are the actual elevations along each one of these arcs. And if you go and have a look here, let's say 100 kilometers from the apex, there, 100 kilometers. You look at the envelope of variability of the topography, and it turns out that the whole arc lies within plus or minus 2 meters of a perfect surface. There's almost no relief on this thing. It's absolutely smooth. It's just the most amazingly smooth surface. And you see on each one of these things, there's very little relief here. So the delta is actually very, very smooth as a conical surface, almost as smooth as a theoretical surface. But there's a lot of small relief, and that, of course, is very important. Another interesting thing is the rivers that we see on the delta, like the Ngqoka and the Nanachera, those rivers don't necessarily lie at the low points like you'd expect. They often sit on high ground, you know, like here, for example, the Mount Jerez sitting way up on a bump here. Okay, and that's another very interesting